today is going to be symmetry-protected. Okay, welcome back. So yesterday, the second half, yesterday's lecture was about the transmission easing model in 1D and its connections to the desired chain. So this is the transmission easing model and the notation that we have. We have the ferromagnetic interaction, positive J easing line, and we had a transverse field. And of course, there are these two phases. When J is largest compared to lambda, the sigmas want to align in z direction next to each other. If the lambda is large, it's just a field induced current, or fully polarized state. So there is no spontaneous symmetry breaking on lambda fields. This system has a symmetry, something that we also discussed. The symmetry is generated by the product of all sigma x's. And that's an operation that flips all of the spin direction. C is your quantization axis. That's because here you have two sigma z's, they both change sign, and then the term is also there. Next, we had a non-local transformation, which is the quantum version of Fermat's-Valier. And we introduced these new objects, mu z and mu x. And as you see, mu z is extremely non-local. We put them on the bonds, and the bonds have these half-of integer numbers. So at bond number 3.5, which is this one, we had the product of all sigma x's before 3.5. Very non-local. And similarly, we had this is a local operator which is just containing the two sigma z's around. We have mu x at 3.5. And from this example, you can see that these two guys actually anti-commute at the same bond, and I also discussed that they actually commute otherwise. So the mu z and mu x have the same commutative algebra as the sigmas, and what we also saw is that essentially when you write this Hamiltonian in mu z as an axis, what you get here is mu x, and here you get the mu z interaction, modular boundary conditions. So there is this transformation by Fermat's and Valier which flips the role of J and lambda. Then we switch yet to other degrees of freedom, which are actually the actual fundamental degrees of freedom in the problem. And these are these Majoranas, which are obtained by gluing an extra sigma z on the right of the mu z. So it's the product of the disorder operator body. Yes.
And why do you say it's a fundamental?
Oh, in the sense that these excitations are the ones that don't decay, really exactly.
That don't what?
Don't decay. So these are sort of so this is a free Fermion Hamiltonian. So okay, there is one more basis transformation that you have to do, the Fourier transformation. But once you've done that, you have diagonalized the Hamiltonian, and in this sense it's fundamental excitations. Okay. All of these zetas are Hermitian. All of these zetas square to 1, and unequal zetas anti-commute. That's what we call Majorana fermions. And then we rewrote this Hamiltonian in terms of these zetas. So let me illustrate this again in colors. Let me use these two. So we had the J term. And the J term is a term with, okay, so the double prime is the green, one prime is red. I changed colors since yesterday, I hope it's not a big problem. Mostly I don't remember which color I used yesterday. So this guy here is a hopping of Majoranas across the boxes. So what you can see here, each box represents one qubit, and we've written each qubit with the help of these two Majoranas. And the J is hopping across the boxes, and the lambda is hopping within the boxes. And then the two limits, so the two we discussed yesterday, and I wanted to repeat this briefly because I was sort of rushing through it. The ground states in the two limits for either j equals 0 or lambda equals 0 encode, well, there is the ground state where the lambda wins, then the ground state is unique, but the ground states where j wins, so you have two ferromagnetic states, the degeneracy is encoded in the edge states of this Majorana chain. So what I was saying yesterday is, first of all, for any I zeta 2, these guys guys being Majoranas, which are distinct. Zeta and zeta are just some Majoranas. I could also call them beta and alpha. So whenever you have this, since these guys are commutative square to 1, the square of such an operator is 1. Which means that if you go to its eigenbasis, this operator is plus or minus 1. I'm not sure if this is a good notation, but this means eigenvalue is off. Okay. Next, I discussed the ground states. In two cases. One of them was j equals 0. J equals 0 means we have only this guy. That means that we have here this combination I zeta n prime, I zeta n double prime. And we should just diagonalize each of those to each n. Right? So the ground is given by I zeta n prime, zeta n double prime equals minus 1 for all n. So n equals 1. I'll write out 1 from 1, n from 1 to L. That is the ground state, given that lambda is positive. If lambda is 0, now note that, yes.
Sorry. You were just saying that the spectrum of Majoran operators squared also equals 1. So the spectrum of each operator is also will be plus minus 1. So
Is that what you said?
yeah. How to
The reason is
how to write the agent state of product of two different operators in terms of agent vectors of each one.
yeah. So okay. So that's actually a little bit more tricky than what I said, because what we did is we started. Each box here is a qubit, right?
Okay.
Or a spin 1/2. So each box is a two-dimensional Hilbert space. Indeed, we write the two-dimensional Hilbert space with the help of these zetas. I somewhat mentioned that the Hilbert space of each zeta is only square root 2. So while I use the statement that when you take two zetas, like for example the two zetas here, which are the ones within one box, they together is I times zeta zeta prime, or I zeta n prime, zeta n double prime. This operator is an operator that acts in this two-dimensional Hilbert space and squares to 1, so it's plus minus 1. Each zeta by itself is in a Hilbert space which is smaller. So it doesn't follow from the fact that zeta squared equals 1 that it has eigenvalues plus minus 1. I don't think it makes sense to write eigenvalues of it. I think that's fine. Question?
So it's quite hard to transform the values of agent vectors of each theta to the product of different.
Well, I would like to write eigenvectors in terms of field space.
Okay.
And then I don't know what to do when I should write in terms of just a single Majorana. Actually, it doesn't exist a single Majorana. It always has two, and the goal is to sort of separate the space here. Now here, at lambda equals 0, we have only this one here. Now we pair across the sides. And in the ground state, you want to have this combination. So I zeta n prime, zeta n plus 1 double prime equals, it happens to be plus 1 because there's an extra minus. Now, I also would like to emphasize, this time I wrote out the sum explicitly, this is exact. So yesterday there was a question about boundary conditions, and indeed it's correct that there are subtleties, but here really including boundary conditions is and what we have here is that n goes from 1 to L minus 1. So we have the ground state when the blue term wins is these guys paired up, these guys paired up, etc. But the very first and the very last one that it can draw, they remain unpaired. And therefore, this last object So essentially what you've done now is for the Hilbert, essentially you regroup the Hilbert spaces. Now the actual Hilbert space are these ones, and then there is one very non-local Hilbert space, two-dimensional Hilbert space. Okay. Good. Now let's now we continue with something that I didn't do yesterday. Right. I wonder whether I should write down let's write down pairing as well. So one can further group these Majoranas. One can further group these Majoranas into complex and regular fermions. So Zn is zeta n prime plus I zeta n double prime over 2. And the Zn, there is also a Zn dagger, they have regular fermionic anti-commutation relations. And so they anti-commute at different positions and they anti-commute to 1 at the same position. And with the help of this, we can actually also rewrite this Hamiltonian in terms of fermions. So with these, H equals minus J, sum goes from 1 to L minus 1, Cn dagger, Cn plus 1, plus emission conjugate, minus J, sum over n goes from 1 to L minus 1, Cn plus 1, plus emission conjugate, plus 2 lambda, sum over n goes from 1 to L, Cn dagger, Cn minus 1. This is maybe the way that you know the type chain. I mean, maybe this is how it's usually introduced. So there's a hopping term, and also this guy is like a pairing term. So it's Cn, Cn dagger, it's nearest neighbor pairing, it's spinless fermions, so you cannot pair them on the same site. This is like a one-dimensional version of p-wave pairing, and then ultimately you have this here, which is something like a chemical potential. Okay. Now, this was open boundary conditions. Let me briefly also discuss closed boundary conditions, so that you are reminded. I guess most of you know this, but still it's a good reminder to see what topology means in momentum space. One can, I guess everybody knows how to define a Fourier transform from this one, and you can infer a Fourier transform for the Majoranas. Majoranas being real have a property that the Fourier transform relates the Majorana momentum P to the one that momentum minus P. Leaving these details aside, let me just write down cooperative boundary conditions. Maybe everybody asks, who has ever seen the discussion to the type chain? Actually, less than that. Okay, so I maybe should go a little bit slower. Good. Fine. Okay, so Fourier transform. Okay.
Could you again explain the Johnson term?
Yes. You mean the fermionic expression? Okay, so now each box is a usual fermion. And there are these terms. So the J term introduces two things. Right? We saw that the J term introduces C dagger, let's say 1, C2, and emission conjugate. So it's just hopping of the fermion. You annihilate the fermion at 2, put it to 1, right? And there is another term that also is introduced by J, which is C1, C2. This is like a pairing term, right? In a superconductor, in a regular superconductor, you have terms like this delta, well, usually you write like this, right? Momentum space. Cp, C minus P is a single superconductor, assuming that you know, yeah, that's up and down. If you Fourier transform back, it's going to be one side, right? So usually it's one side, given that it is one side, it has to be antisymmetric in something, it's antisymmetric in right? In this situation, these are actually spinless fermions that we introduced. So we had here these Majoranas, and each Majorana, these two Majoranas have been now combined into fermions. Again, fermions, of course, each fermion has a two-dimensional space, cavity or right? And they are, however, these guys are spinless. So I cannot pair spinless fermions in the same way that I usually pair electrons in an S-wave superconductor. So this is an unconventional superconductor. It looks like a mean field model for an unconventional superconductor. And hence all this discussion on proximity-induced superconductivity. Then there is the last term, the lambda term. Lambda is just C dagger, in this case 3, C3, right? And that's just a chemical potential. Chemical potential is called minus lambda. So when you have a usual Hamiltonian, you write minus number operator, no? Minus mu times number operator. And here instead of minus mu, you write plus lambda. Okay. When you Fourier transform this, let me emphasize again that now this here was for open boundary conditions, and this mapping is exact for open boundary conditions. And now I take whatever I got out of my mapping, this thing here, and just Fourier transform it under the assumption that now I take periodic boundary conditions. So H equals dp over 2 pi I j z prime zeta prime of minus p zeta double prime p e to the ip. I set the lattice constant to 1, and this goes from minus pi minus I lambda zeta prime minus p zeta double prime of p. This is on site, so there is no such extra term. This extra term is what you get when you Fourier transform operators which are adjacent sites. We can also write it like this: half integral dp over 2 pi from minus pi, and then you group these guys into some sort of, you can call them some sort of non-boost spinners or so. Minus p and zeta prime, zeta double prime at the moment of p. So we have this term which is one side. For example, we have so the over or minus sign in front is converted. So I have I lambda here, and here minus I lambda. So zeta prime minus p, zeta double prime p, that's exactly this one. I get minus I lambda, so plus I lambda. And then I get a second term. Here I have written it, I've taken an extra factor half because I've written it as zeta double prime minus p, zeta prime p. Swapping these two guys gives me extra minus sign, and I have minus I lambda p. So that term is this term. And then there's a term from here. So again, the one which is, I can read off what I have here, but just looking at what I have here. So I have minus I j e to the I p. And here I have I j e to minus I p. Minus I p. Okay. So this Hamiltonian is block off diagonal. And it actually makes sense to write this Hamiltonian maybe now I should emphasize this. Everything that I've done was very much in sort of second quantized language in terms of fermions, so it's really designed for many-body physics. And most of what I do here is discussion of topology in the sense of many-body physics. However, I will briefly now discuss the topology on the level of single-particle Hamiltonian, and then we get back to more general situations where you have interactions, so many-body physics is necessary to discuss. So this guy here, in this bilinear of fermions, this is your single-particle Hamiltonian. And it's, in this case, it's useful to write it like so, write it as V of P times sigma. So sigma is a, oh maybe we call it sigma, I already used sigma over there. Let's call it tau. So tau x, tau y, tau z vector. And the V of P that you can read off has a very special structure. It has zeros. Third component, the first component is sine is j times sine p. The second component is cosine j times cosine p minus lambda, then 0. So this is with matrix a fun in polymatrix. Now, we discussed these ground states, etc., and the appearance of Majorana edge states so far in the real space picture. But there is this idea or this concept of bulk boundary correspondence, which actually tells you that there is, for closed boundary conditions, the momentum space topology is not trivial. So it goes hand in hand. You have a non-trivial momentum space topology, and I'm explaining what is the topology, and you have edge states if you have an open system. The topology is the following. The Hamiltonian, the single particle Hamiltonian is just this V of P times the tau, so the energies, there are two bands, and they're just plus minus V of P. So it looks something like this. The dispersion relation of effective fermions. P. You see when P is 0, so okay, so maybe I should say that this here I can calculate plus minus, I take the square of this plus the square of this, so I get j squared from this plus this minus 2j lambda cos p lambda squared. I'm doing something wrong here. You write it on this again. Let's do step by step. This here is plus minus j squared sine squared plus, and then I take the square of all of this, j squared cos p squared minus 2 lambda j cos p minus plus lambda squared. This continues. So then I can combine these two here, and I get, but I can also write it as, it's easy to write it as j minus lambda squared plus 2j lambda 1 minus cosine of p. This is just combining these two. You see this is positive, this is positive. When p is 0, this guy is absent. So then actually this is the lowest point that you have in your dispersion relation. And when p equals pi, this here is maximal, and then the energy is maximal. So the energy transfer should like this. This is at all points except for the situation when j equals lambda. When j equals lambda, there is a touching point. Here. This This would be the dispersion relation for J with lambda. Because then this goes to dimension. So actually, as we discussed before, J equals lambda is special because that's the position where the model is self-dual. And what you can see from here is that in terms of our fundamental degrees of freedom, our fermions, the model is always capped, except at the special point which is the phase transition. And at the phase transition, the description is effectively given by this sort of Dirac equation. And from this you can, I mean, this is a free fermion problem, you can relatively easily extract critical exponents for this quantum phase transition between J wins or lambda. I'm interested in staying away from this point so that we have a gap. Then we just fill one of these lower bands. And what we can ask is, what are the properties of the mapping? And that's now where the momentum space topology comes in. So I write the momentum space topology. Momentum space topology. That's due to the mapping again. So we have this mapping P goes to V of P, which is a mapping from one sphere, right? Because the Brillouin zone has currently boundary conditions. So it's like a one sphere. And when we assume, so this is for J non equal to lambda, when we assume that we are away from criticality, this V of P here is the vector which lives in the two-dimensional plane, because we know it's actually symmetry reasons that the last component is 0. So it's a two-dimensional vector, but it cannot be at the origin. We already know it can never be at the origin. So this here is going to be R2, except its origin. This is where my curly brackets case for that. Okay. So this is a mapping. Let me draw this also as a picture. This is a mapping from the one sphere to the plane where I remove this point. Yeah? And it turns out that in the plane, this mapping can trace different types of curves. Right? So what you will have is this is a continuous mapping. So in the plane, let me not take again, let's say, blue. Orange. So there's a situation when the mapping is such that, so first of all, the mapping is continuous. You start at some point. You start at this point here, this is mapped here. The next point is mapped slightly away or so. In this situation, when lambda is larger than J, the mapping is such that you're not enclosing the origin. In fact, the mapping is a very simple circle, but in principle it could be also something more complicated. Let me just finish this one part. So this would be the situation lambda greater J. And then there's a situation when lambda is less than J. You also have a continuous path, but now it's different in topology because it encloses the origin. That's right. Yeah, lambda J. So there are two different topologically distinct situations. Knowing that the gap Hamiltonian has a mapping which excludes the origin, you can ask the question, are you winding around the origin or not? And that's it. Yes?
What is it in the question that we exclude?
The origin. So,
Elio, could you repeat the question because sometimes
yeah. The question was whether, what's the reason that we excluded the origin? So, the spectrum is gapped everywhere except at this quantum critical point where J equals lambda. What we want, so the quantum critical point distinguishes two phases. In the language of the sigmas, these are symmetry-broken and non-symmetry-broken phase. In the language of fermions, these are these topological phases where you have S state or not. We want to characterize now the phases, not the phase solution. The phases are gapped. Remember that I gave you as a fundamental ingredient for topology, and in particular also symmetry-protected topology, I gave you a fundamental ingredient that these are gap states. So I want to consider the gap situation which means that this V of P here is finite. It never touches the origin, as long as J is not equal to lambda. So then, since we have removed the origin, we can ask the question, okay, the smooth curve that I'm tracing this V of P as I'm going through the Brillouin zone, does it enclose the origin or not? And this is the way to distinguish the topological and non-topological situation in momentum space. The first question there.
Yes. Sorry, can you explain this analogy with sphere? I mean, sphere on the R2, so the R2 is just the space where the vector lives.
Yes,
right?
Exactly.
And the sphere, you mean?
That's a Brillouin zone.
Just the Brillouin zone.
Zone.
Just the momentum space?
Yes.
Okay.
Because P is periodic.
Yes.
In higher dimensions, this becomes a torus. Because you have two spheres.
So we remember from the last lecture that the model is actually dual, and what as we know, with this means that kind of topological and trivial phases switch roles. How do I see this from this picture? So what kind of mapping I should apply to the image of this curve to see that now let's say the blue curve becomes trivial?
Okay, I'm not prepared for this question. What you see is J and lambda in terms of fermions. What they do is they define intra-cell hopping or inter-cell hopping. Who told you that, I mean, forget about everything I heard about the qubits, but who told you otherwise that I should draw my boxes like so? Maybe I should draw them like so. So imagine I have closed boundary conditions. In the case of closed boundary conditions, I can do this, I can define them differently. And that's essentially the operation that you have to do, at least in real space. I should say that actually, so this is my Ranas. There's a model which is very similar to this, which is, you might know, the Symmetry-Protected model, which is with complex fermions. And people stopped calling these hierarchy topological insulators in that context. They call this atomically obstructed insulators. Okay, you know them pretty well. What do you notice? What was nodding at this fact? You know it?
I understand what this implies because, well, I kind of know the Symmetry-Protected model.
So their logic is that essentially the usual atomic insulator is when you have your Wannier states and ground state all sitting at the side of the atom, or in this case of the box. And then there is your atomic obstructed insulator, which is when the Wannier states sit in between boxes. Okay. Did you also have another question? Or is it?
Why is the origin inside the loop when lambda is smaller than J?
Sorry.
Why is the origin of the coordinates is inside the loop when lambda is smaller than J and it's not when lambda is bigger than J?
Okay. Actually, one can just take this thing here and plot it. Let's do it. I mean, I just showed you sort of conceptually. Let's say lambda equals 0. You agree that this thing is parameterizing a circle around the origin? Okay, good. Imagine J is 0. You agree this is just one point, lambda? So it would be just sitting somewhere minus 1. So just sitting. And then as you increase J, the circle becomes bigger, something.
So now we consider on the model, and formally this is, so how we distinguish two cases by fundamental goal. Yes, so we can close circle or not.
Yeah.
If you go to highest dimension, it will be highest construction goal.
That's yes. So there are different situations. So there is a table, I didn't plan to speak about this table of topology first, but essentially that's what it is. You have, in higher dimensions, well, I said that the Brillouin zone in higher dimensions is a torus. However, and that allows, then there are different kinds of, okay, let me just show you this. You have a mapping from a torus. This is your breadth, this is px, let's say 2 dimensions. Dy, I draw a torus. This is torus. Okay? And now maybe you have, instead of having a 2 vector, let's assume V of P is in R3 except, oh, this is the wrong sign. This, except 0, right? So you have this 3 vector. And now essentially what you could ask, which is the 3 vector without the origin is yeah, it's essentially the same as the two-sphere in terms of homotopy groups. So essentially you can make this a unit vector that's normalizing it, that's what I'm saying. So now you want to place a unit vector anywhere here. And you can ask a question about the various topologies that you can have. Clearly at the edge, here and here, this vector has to be the same. Here, 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 etc. Right? Then there are different configurations. You have a situation that, let's assume that the vector is just the same everywhere on the edge. And then there are possibilities of having windings such that in the center the vector goes inside, everywhere outside it goes out. It looks like, do you know what a skirmion is?
Again,
Do you know what a skirmion is?
experiments.
Okay, so there is topological, I'm drawing out a topological configuration for you, which is non-trivial.
Yeah.
Which would be everywhere on the boundary, the spins point out. So this is like a spin. Let's call this spin or this is a unit vector. V of P, it's just two-dimensional unit, right? That's what I'm interested in. Given that this is the origin is excluded, I can always normalize it. This unit vector can point out everywhere on the edge, and then you can ask the question, oh, does it go inside in the center? That would be one topological configuration. So if your effective vector in the Hamiltonian is of this type, you're actually categorized with a second homotopy group. That's okay. But then there are also different situations. You could also have a situation which is again similar to the one that we have now, which is this. And you can have cycles like so. These are called, well, so the previous ones are the strong topological insulators. The ones that I just said are either weak or crystalline topological insulators. So they are due to the properties of the fact that the granules are actually toys. So yes, but in any case, you can generalize it to higher dimensions, and of course it's an art on its own. Many of these topological, strong topological insulators have been classified in the late 2000s, all of them, and beyond that, I think people are still working crystalline topological insulators, early 2010s, I guess, but people are still working on some aspects of how to wind what around what, and what are the various topological invariants. Hopf insulators and Euler form and all these various possible topological things that you know from the differential geometry.
Yeah, okay, so first of all, I would like to point out that it's not exactly the sphere because for my runners we have the mention that fermions of pi is conjugated to fermions minus pi. So it's not an arbitrary mapping here, it should preserve some symmetry.
Yes, that's right.
And
so there are symmetries related to this.
Yeah. And the second point is that you're talking about phase transitions in the systems, and you pointed out that okay, for the one point you have edge modes, for the other point we have this integral topology, the fermion spectrum. But like it could be the consequence of phase transition. Yeah. So you also talked about the conjecture that they're linked, but you did not
explain. Yeah, I did not show it. This is true. I'm just saying that there is something called boundary correspondence, and I didn't show that this is something following from. I just gave evidence, one evidence, that it occurs here. Yeah.
The question about the underline for along the larger and smaller case, because you now draw in the same direction, so actually correct.
I think they actually go the same direction, but maybe I do the direction wrong. Well, it depends on how I draw the direction here, obviously. Right? I think here they would go in the same direction, because ultimately they come from this way. They come from the fact that this is parameterizing a sphere, which is essentially centered around lambda, or minus lambda. Okay. So, good. So we discussed the appearance of these X-rays. And yeah, okay, I think this is essentially what I wanted to say about the details of the entire model, and I was going to use it now to introduce symmetry fractionalization and the connection to transit degeneracy. This is actually a method that goes beyond single particle physics. So what we just discussed here These are methods which are applicable when you have free fermions. And then you can start to hide. You use Bloch's theorem essentially, and then in momentum space you start to look at all these mappings from the Lagrange zone to whatever the manifold is, which is spanned by Now I would like to do something which allows us to go to the interacting phase. I'm still using the same example that we have, but you will see that this is based on general arguments of symmetry, and therefore can be generalized to interacting systems. So this is chapter 2.3. Symmetry. And symmetry fractionalization. So I mentioned before that there is a symmetry here, and the symmetry, yesterday I called it Q, which is just a product of all sigma x's. In terms of fermions, so it is conventional to call it Q, because it's a conserved charge. In terms of fermions, however, the symmetry is typically called P, but it's the same symmetry, just related by this transformation. And it's the product of all n, independent of whether you have closed or open boundary conditions. I will mostly discuss open boundary conditions now, but in principle the symmetries are also for closed boundary conditions. This is the fermionic parity. The fermionic parity obviously commutes to the Hamiltonian, because you cannot write down Hamiltonian as an odd number of fermions. In fact, this leads into the discussion whether one should consider the Klein chain as an example of a symmetry-protected topological phase, because the symmetry is so fundamental that there is no way of breaking it. We will see, however, that we can still extract typical aspects of what's used in the context of SPTs, of symmetry-protected topological phases. So let's just use the same convention and study what the consequences of the symmetry, which anyways cannot break. Okay. The fermionic parity squares to 1 because each of these factors squares to 1. As you remember, this is a combination of two Majorana's, this extra I just squares to 1. Alright. So it's conserved. That means equal-mutation. Good. So, okay, so it squares 1. So P squares 1. So that means that there are two sectors. P equals plus or minus 1. In one case, you have an odd number of fermions, and the other case, you have an even number of fermions. Right? You can have a ground state with an odd number of fermions. No problem. Okay, and of course, you will never get from an odd number of fermions to the sector with an even number of fermions. Just block diagonalize the big Hamiltonian. Good. Now, this concept of symmetry fractionalization.
Sorry,
Yes.
question.
Yes, please.
So, do you understand correctly that it actually counts the fermionic parity, and if I will act with some kind of operator that counts the number of electrons, and if this gives us an odd number of electrons, then we will have one by acting on the same state with this fermionic parity operator, right?
So that's right, but okay, maybe I should have emphasized this.
I'm just asking about the name.
Yeah, no. You cannot count the number of electrons because the number of electrons is not conserved.
Ah, okay.
It's only conserved modulo 2. Because it's modulo 2.
Ah, yeah.
Because it's a superconductor. Yes. Right? So therefore here we only have the Z2 symmetry.
Okay.
Right?
Okay. Good.
But I also mentioned in my talk yesterday that the integer quantum Hall effect can also be seen as a symmetry-protected topological space. There you have a U1 symmetry because number of elements is conserved. And again, there's the same debate. Is this right to call this a symmetry-protected topological phase? Because, well, we have just U1, particle number conservation is so basic. I mean, how you can break it when you make a superconductor, but otherwise no. And so that's why also people say integer quantum Hall effect, maybe not a symmetry-protected topological phase. Sometimes it's called an invertible, also an invertible topological phase, which means that you can undo it. Let's say with the quantum Hall, you can put a quantum Hall nu equals 1, and a quantum Hall nu equals minus 1, and you can undo it. So nu equals 1 and nu equals 1 together is nothing. So that's something similar here. You can undo it. That's okay. People call this invertible phase. But for simplicity, let's all put this into the bucket of symmetry-protected topological phases. And in the quantum Hall effect, maybe you know, you have this edge anomaly. Yeah. So this is in principle, it's very similar to, or something very characteristic of symmetry-protected topological phases. And similarly, this one is symmetry fractionalization, which is actually particularly good to use in one dimension. It's also characteristic of symmetry-protected topological phases, despite the fact that here the symmetry is so fundamental that you can anyways not take it. Okay. Now, so the point of the symmetry fractionalization is that we have a symmetry in the ultraviolet, that means in the original lattice model. And we want to know what are the properties of the symmetries in the effective low energy theory. So as always, in the context of many-body physics, well at least oftentimes, we want to know what's the long wavelength behavior, etc. and so on. And we want to see emergent behavior. And similarly here, we sort of project now to the low energy subspace, or to the ground state, or the ground states. And what we'll see is that the symmetries act very non-trivially in the topological case. Yes?
Why did you say that this is symmetry in the ultraviolet?
So this is an exact symmetry. But I will now use the symmetry to get an effective symmetry operation in the low energy subspace. So this is just a symmetry. No, period. There's nothing extra to say about it. This is a symmetry, but now I want to get an effective symmetry in the low energy subspace. And now we can use that. There are these two different cases that we discussed. Yeah, so for the trivial case, and let me go again to the limiting cases. The trivial case was lambda, was J equals 0. We see that these guys here are always minus 1. Okay, so now this is a little bit impractical that I have this combination here. But in any case, we have, let me leave it as this. We get P equals minus 1 with the L. It just happens to be that it depends on the number of signs. Right? We have minus 1 factors. Minus 1 L times L factors. In the topological case, what you see here, so this was lambda equals 0. Actually, again, I have this vector minus L. This is just because my choice was maybe not ideal. You can disregard the minus 1 here. It's just an extra case. Here now, you have all of these factors. So you start from zeta 1 prime, zeta 1 double prime. The next one is zeta 2 prime, zeta 2 double prime, etc. And in the low energy subspace, you can pair these guys up on adjacent sides. So what you're essentially left with is up to a prefactor, which is in this case minus 1 to the L minus 1. You have additionally I zeta 1 prime, zeta L double prime. This is essentially the unpaired, the non-local qubit that we have in this problem. So the parity operator effectively, this means, let's put a dot here, this means it's projected to the low energy subspace. It now has two contributions, one from here and one from here. So let's write this here as, this is the first side, this is the last side. Let's call this P left, P right. So the parity operator in the low energy subspace is actually the product of two operators. One of them living at the left edge and the other one living at the right edge. Okay. They have the same property. So the P's, the PL and R, both square to 1. But clearly, PL and PR have a very good algebra. They actually anti-commute. So it's a symmetry operation which acts non-locally and moreover has a weird commutation statistics. That's actually the fact that they anti-commute is characteristic for fermionic HPTs. But the fact that there is such a fractionalization of symmetry is something happening on one edge and something happening on the other edge, that's typical for SPTs. And moreover, if you have such a situation that your symmetry is fractionalized, so you have this operator, this overall operator, this commuting with the Hamiltonian, it's fractionalized, these guys fulfill essentially a Clifford algebra. You can conclude based on symmetry arguments that there is a two-dimensional low-energy subspace. So if you just take your P, you project it to something without knowing what it is. And then afterwards you realize, I have symmetry which is acting non-locally, and these two symmetry operations are anti-commuting, you can infer from this that there must be a two-dimensional subspace. So you can use the symmetry to infer the ground state.
First, how do you once again define the L and the R?
Good question. So first of all, it's very impractical that I call the chain length L, and I use L for that. So L inside,
that's 1 and L,
right.
1 and 2.
This is 1 L. So that side 1 is on the left edge of the chain, and L is on the right edge. And then unfortunately I use L and R also to work. I mean, if you want, we can use lowercase L and R or something.
Contribute a square root of I to each of them also.
A what?
A square root of I.
Okay, I didn't say anything. What exactly is? I mean, also there's this factor. Yeah. This factor is someone too. It doesn't really matter which phases you can absorb wherever you want into either of the two. Okay, so now we're going to define.
Sorry, last question. So I thought about that in a way that okay, I have some kind of specific state with some specific number of fermions, right? And I act as my operator, and it counts the pairs.
Yes.
Right? And here, in the trivial case, we have P, which is just minus 1 to the power of the L.
Yeah.
It doesn't really depend on the specific state.
Exactly. Yeah.
So I'm a little bit confused.
So this just means that the parity is always, in this case, well, the parity depends on L because I have L boxes.
Yes.
Essentially, what the ground state means is occupied on each box.
We're talking about that. So when you write like P equals to minus 1 to the power of L, you mean that we act with P on the ground state?
Yeah, that's right. So this
so this is acting on the ground state.
This dot means, so this is a projection on the low energy subspace, which means on the ground state or ground states.
Okay.
Yeah. So yeah, so that's why I said this is a U, this is really the symmetry in the UV, and this is sort of the effective way the symmetry acts in the low energy subspace. Okay, so let's how do I proceed? Yeah, maybe we keep this on this side and I go here, so that we can still see what's written right. Okay. So I wanted to define this symmetry fractionalization. We do need it later as well, so we'll do it up there. It's not important. It's the same as you just said. It's independent. I mean, it's just
Okay, it sounds like some kind of, well, I don't know, general basically.
yeah, it's just space. And maybe if I highlighted this minus one to the other here because you have something, without J, let's say first triple case. Without J, here you have number conservation. And then it means you have like occupy on each of these blocks. And also similarly you occupy between these guys. This gives us minus one together. But if I had chosen things maybe more wisely, then it wouldn't have ever appeared.
Because like it sounds like this is some kind of bulk property, which counts actually the number.
Yeah, it happens to be so that the bulk maybe knows about the number of bytes in the way that I can learn the number. But yeah, has no specific meaning. The important information is that there are these operators, the topological case has operators which live on the edges. And that they have a non-trivial, in this case even a non-trivial anti-condition relation, in general a non-trivial representation of symmetry. And that's what I'm going to.
But this talking about edges really only makes sense if we have orthogonal dimensions.
Yes, and also in one dimension. In two dimensions it's more complicated. So actually in two dimensions I would have probably rather resorted to these field theoretical anomalies. I think of these as essentially two different ways of describing the same thing. And I felt this is sort of more accessible in this on the left. So let's define the symmetry fractionalization, which is really sort of characteristic for SVD phases. Symmetry fractionalization, symmetry fractionalization. So what we do is we look at gap system, length L, and the situation where we have a unique ground for periodic boundary conditions, but we want to look at the situation of open boundary conditions. No spontaneous symmetry breaking, no spontaneous symmetry breaking. Okay, global symmetries. Global symmetry. We call them, there is a set of them, so there are a set of these U's. And these U's act on each local Hilbert space. So it's a third product of all the n's from 1 to L, U and that's the product of all of unitaries acting on each, let's say, qubit or so. And now, what we have for open boundary conditions, we have in the lower energy sector, so let's notice again that it's not. This behaves like UL times UR. This is allowed in the low energy sector. UL and UR act on the left and right edges, and the overlap of these operators vanishes as goes to infinity. X on left edge, X on right edge. What you see is that imagine you have two different operations, U1 and U2, so, and they have a certain algebra. Maybe U1 squares to 1. Then UL can square to e to the I phi if UR squares to e to the minus I phi. So that means that actually the representation on the left and on the right can just separately can be more general than the original symmetry was. This representations when instead of having UL squares to 1, you have UL squared equals to e to the I5 or something like this. These representations are called projected representations. In this case, it means representations modulo a phase. Okay, we will see an example of where something of this type happens. Yeah? So,
so what is actually the definition?
what is the definition of what? I'm not done yet, but yeah. Well, the definition is going to be, so first of all, what I wanted to say is that may be protectively, so symmetries may be protectively represented. Projectively, and we will see an example represented. That means modulo phases. Okay. And now that's actually the situation. So the symmetry fractionalization is this. The symmetry is fractionalized into left and right.
And this acts on the ground state without spontaneous symmetry breaking.
So we assume that there is no spontaneous symmetry breaking, and this here means low energy substrates. This stuff, which means essentially ground state manifold. So which other colors do I have? I had green somewhere. This means low energy substrates.
But again, the no spontaneous symmetry breaking means that we choose parameters such that the ground state is not.
Yes, we do assume that we have no, we choose the parameters that have ground such that we don't spontaneous symmetry breaking. We are interested in symmetry-protected topological phases. So therefore, we are only interested in a situation when the symmetry is still present. Okay, so now essentially, so the definition of symmetry fractionalization is that this happens. And the definition, or the way that we use it is that let me write it out as I have here. The algebra of fractionalized symmetry operators defines the SVT phase. Where SVT is of course symmetry-protected topological phase. So in particular,
so the fractionalization itself is the fact that we require, or it just follows from what we ask?
So the fractionalization is that your symmetry can be written as such.
I mean, if we have a system that
allows
the features, then you fractionalize as UL and UR, right?
That is, well, I would say it this way. Symmetry fractionalization means that your system, your ground state manifold is such that your NEU can be represented as something acting on the left and something on the right.
Yes, exactly. I mean, you listed a number of features
Yes.
of our system. Do I understand correctly that if I have a system with all those features,
yes,
then
then
I essentially have this symmetry fractionalization?
Yeah, this is symmetry fractionalization. That's right. So these are the defining things of symmetry fractionalization in an SVT phase. This means SVT phase, I guess. Right. And then we use the algebra of the UL and the R to define the SVT phase.
Okay.
In fact, you can uniquely characterize all the SVT phases if you know what are the allowed ULs and URs. We will actually see how there are constraints on them and what's allowed. Okay. So for bosons, maybe I should highlight this one. bosons and for fermions. So for bosons, ULs, all of the ULs, and all of the URs commute. This was not the case that we've discussed so far, but well, maybe today we will manage to get also to the situation which is done. And then all, okay, this is one step. Okay. Then we have, so the edge is essentially completely decoupled, right? Let me write this in color as a comment. This means edge is decoupled. The ULs form same algebraic group relations as the original used modulo phase vector, right? Modulo phase vector. That's this protected representation. So this is this. This is this. And of course the same equivalently for the right. For the set of U rights. So you can have, on the left edge, we will have an example where we have rotation invariance. It's a spin system with rotation invariance. Originally, you have the full system with rotation invariance under SU2 also, or a subgroup of SU2. And then we will see that sort of in the low energy sector, we will have the rotations at the edges, but the representation is somewhat different.
What do you mean by for bosons?
For bosons means that we have a system which has only bosonic degrees of freedom in the beginning. For example, spin chain. So commuting degrees of freedom.
So this Ising chain is
the Ising chain is by itself not an example for an SPT because it's an example for a symmetry breaking chain. When we write it in terms of fermions, that's the next point. For fermions, there is an additional step, namely that the UL and the U right not necessarily commute, they can anti-commute, as we saw here. Yeah.
But I don't know in advance what kind of statistics for the excitations I have. So I have spin chain, I can apply, I don't know, fermionize them, bosonize them. So what exactly defines how? Is it, maybe it's actually the way to know the correct excitations if I have a topological phase, at least to know the statistics, or I don't know.
Yes, in principle that's the way that you could say it. If you extract from somewhere the ULs and URs and you check whether they commute or not, you can essentially infer it. You can say this way. There was a question. What did you done?
Maybe I missed the question answered. Again, the mathematical statement is that if we write the effective symmetry operator for the ground state, all the UNs that are not left to right kind of cancel out, collapse to the face, and then the left is just UL and UR, or this kind of feature, which is a mathematical statement that can be left.
Yeah.
That's
it, yeah. So everything in about sort of cancels out because it's sort of, but then it might be that something is left over.
Okay.
So as in this example, indeed. Yeah.
I have a question. So we have that information that we have you, and I give you a projection of the ground states.
Yes.
Can we use UL and UR?
I guess no, because you don't know what's the spatial structure of this state of this projector. You just
Yeah, but we know all U.
So actually, I think, okay, so this is something that I don't use very much, but in this, so this is used a lot by the DMRG and the tensor network people. And I think when they project, they essentially know what they're doing. They're sort of contracting some indices or something like this. And then they would see that something is remaining. Pretty sure that they can actually really extract this. On the other hand, here we just use it as a means, we have what we will have here simple analytically tractable examples where exactly this feature appears. Maybe I should say that here I did it only with the most simple cases. Right? Because as soon as we are going away from this limit, then it becomes a little bit more complicated. You have to look for operators which have only exponential support, and it's less clear. So that means that potentially, in principle, yes, but it requires extra work, and maybe it's not a practical way of doing it.
It's simply not understood. You described the construction of all that for the Ising chain.
Yes.
Now, what happens in, do you mean that there is something more than Ising chain in what you present, and
So-
something more general?
So let me emphasize that what I did here was for the Ising chain represented in terms of fermions. When we really speak about symmetry or topological phase, this is not to describe the symmetry broken phases of the different speed Ising model. This is a construction to describe symmetry-protected topological phases. So let me emphasize again that the two of them are related by non-local transformations. So therefore, this was sort of part one. Yesterday, the main point was, one point was to show that there are these some models in which order beyond Landau is actually just a non-local way of writing order in the sense of Landau. But let's forget about the duality. It's just about the Kitaev chain. Let's forget about the Ising chain, just the Kitaev chain. This is something that is trying to introduce concepts which allow to define topology even beyond the single particle picture. And in fact, we can now, as a next step, include interactions and still see what are the allowed phases. But here, of course, the system now is fermionic from the outset. I have forgotten that I at some point started from some Ising chain.
Yes, but then what would be these proposals?
So for bosons, when you have a purely bosonic system, and we will discuss then probably tomorrow the AKT chain, just spin one chain, then we have bosonic degrees of freedom. So you can ask the question about symmetry-protected topological phases for strong interacting systems without fermions. And then the UL and UR will just commute. Well, for fermions, in this example, the anti-commute. So that's the last point. Otherwise, everything is the same, but the UL and UR anti-commute. Or need not commute. Maybe I should write this note as need not commute. Can commute. Depends on which operation, I guess. So the fermionic symmetry is can commute. Okay.
I don't get it. What's the eventual statement? They should not commute,
No, there's an example here with the anti-commute.
they anti-commute, but you kind of wanted to say that there can be something else except this.
No, well, they cannot commute. There are potentially symmetries which act locally and don't do anything on the other side. There can be fermionic systems where you have an operation which is acting on one edge without doing anything on the other one.
Okay, which means
they wouldn't be commuting.
Okay, and for basically for fermions it can be whatever. Just that they should be local. They should be local, and that's it.
Yeah. Yes, but you still have the situation here. So all of what's written here still applies, so you can have this algebraic group relation of the space vectors.
Okay, this I get.
But then, in the case of bosons, it is completely decoupled. In the case of fermions, there are statistics which can sort of non-locally let the edges speak to each other. That's all I want to say at this point.
Okay.
So maybe the first, maybe that's also why we have this first. So the bosonic case is a simpler situation. The symmetry is completely, the edges completely decoupled and have their own projective representations. In the case of fermions, we have to keep in mind the potential statistics connecting the edges. So let me continue here. Yes.
One more question. And then you basically say that there can be no other type of excitation except like bosons and fermions. So
okay, maybe this is the right moment to announce that there is an exercise sheet which is online, and you will have power fermions. So the exercise sheet is essentially redoing what we're doing right now, essentially everything that we've reached until here, but instead of for the easing chain, do it for the clock chain. So you have clock variables, and you will find that instead of having Majorana fermions, you will have parafermions, lattice parafermions at the edges. To find the exercise sheet, you go online, you look for the, so somewhere there's my name on the website of the school. If you click on it, you will see the outline of the lecture. And now, on top of the outline of the lecture, there is a link to exercise number 1. Okay. And the exercise, so as I said before, the exercises, I won't discuss them here, you can just ask me. And as I will upload my lecture notes step by step, I will also include the solutions to the exercises in these lecture notes. So probably like on Thursday or so, or on Friday, I will upload, or I will ask Galina to upload the first chunk of my lecture notes, and then you scroll down in the lecture notes, and you will find somewhere this exercise. Good. So more about the time-like change. And in particular, more about symmetries in time-like chains. So the purpose of discussing the time chain in terms of Majorana, in part, was to expose you to this idea of this symmetry fractionalization. But of course, we've done it for a model where this is an overfill. We can solve the model also without any of that. So now let's see what we can learn from this for more complicated systems, and that's the Z8 classification. This in part goes back to your question in the back. You asked about more complicated mappings in the momentum space with the Hamiltonian space components. There is not only the situation where you increase the dimension of the momentum space going to higher physical dimensions, but you can also change, make the Hamiltonian, the effective thing with the Hamiltonian is more complicated and bigger.
Number of parameters.
Number of parameters, yes. Which allows in particular also in this mapping where you go like from the one sphere to the plane without the origin to wind multiple times. And in principle, in this classification of topological insulators, the class where the type chain is in allows for any integer winding, class PD1. Then König came and said, oh, but when we take interactions, actually this classification, which is any integer, goes down to an 8-fold classification. They explicitly constructed an interaction, so what they essentially looked at was, they looked at a bunch of p-type chains, they had all Majoranas at the edge, and then they let them interact. And the question that they asked is, can we find such interactions that the system gets a many-body ground state which does not break any symmetries, yet caps out these Majorana excitations at the edge. So of course, if you have like just 2 of them, right, you can let them can let them hybridize or something like this, and then obviously you get it out. However, hybridization would violate, in their case, they also want to look at time versus symmetric situations, it would violate time versus symmetry, because it has an I. And then they went on to look like what's the first possible way where you can sort of get out this thing. Yeah? And they found that you can put an interaction term when you have 8 such chains, so 8 edge states. And then it's possible to actually gap out the many-body spectrum without breaking any symmetries. And that's why this reduces to Z8. And we're going to see this from the symmetry fractionalization perspective in a second, where the Z8 comes from. Let me just briefly say that this is an instance of what's called symmetric mass generation. So you might remember from your high energy class that we're discussing mass generation of zero energy modes, particularly in high dimensions of Dirac elements. We're discussing something like spontaneous symmetry breaking, so as a means of breaking, of getting a mass. But a mass appearing for Dirac elements usually comes together with breaking symmetry. So that's what goes in the theory communities goes under the name of Cosneville mass. Here, we're inducing a mass in the many-body, a gap in the many-body spectrum without breaking the symmetry. And people have started looking at this also not only in the zero-dimensional situation of the edge of some back chains, but also, let's say, for three-dimensional Dirac equivalents or so. Whether you can you can induce a mass without breaking the symmetry. Okay. Well, there is an interest, there's a connection to high energy physics here. This number 8 is very special, has some deep meanings. Okay. Good. So here we discussed the possible. Essentially, what you can have here is we found here essentially 2 different ways of representing our symmetry. One of them is P left and P right as one, contain this up to a phase. In the other case, these guys here uncommutable weird statistics. This is actually all that there is in the case when you have just 5 minutes, I guess, right? This is all that you can have if you just have this P symmetry, this parity symmetry. Let's additionally discuss what's the impact of time reversal symmetry. So when you have time reversal symmetry, so now we have P symmetry and time reversal symmetry. P is this P. So I don't need to write it again. But time reversal symmetry has this property TIT is minus I, where actually T squares to, in this case we're looking at T squares to 1. And then acting on these C operators that I've erased, T Cn T equals Cn, and T C dagger and T equals Cn dagger. This actually implies that the Majoranas, one of the Majoranas transforms non-trivially. Remember that the C is zeta prime plus I zeta double prime. So that means that T zeta prime n equals zeta n prime, but T zeta double prime n equals minus zeta n double prime. Okay. So now let's assume the following ansatz. Assume fractionalization.
Sorry.
Yeah.
You wrote it by construction.
So this is the definition of what time reversal symmetry is. This is what it does.
Okay, so
all this,
it's act on Cn, you just like derive things. Okay.
All of this here is the definition, and this is the consequence of the last one. And also this. Because there is an I here. C plus this zeta.
What's your T?
T is the representation of time reversal symmetry in the big Hilbert space. And it also, every time you see an I, you conjugate it. So this is like a big unitary operator. Right? So like this one.
No, you go, just don't understand. T, it is written T equal minus I.
tit, oh sorry, this is I. When t acts on I, so if I can do this, still there? But t equals the inverse, so I can just write tit.
So first of all, again, so how does it all fall into like tenfold classification?
It goes beyond.
Beyond.
We're going beyond now. ZA is beyond tenfold classification. Z will be tenfold. Yeah. Okay. So let's assume we fractionalize. Let's assume we are in a situation where it makes sense to write this as left and right. Even in the trivial guide case, you can write left and right. Just in the left and on the right, you just have one. So let's assume we fractionalize. And we represent T as a unitary on the left, a unitary on the right, and charge conjugation, and complex conjugation. So these guys are unitary. This guy makes the whole thing ununitary. So from t squared equals 1, we see that u left conjugated to L, u right conjugated to u right equals, okay, so now it depends. 1 if UL and UR commute. Sorry, just 1 second. Minus 1 if that.
About the definition paragraphs, probably across the whole place, yes, because trivial transformation, but it does not give sign of background.
Can you repeat what you just said?
Oh, probably I'm wrong, but it's correct that it doesn't leave ordinary fermion.
It does not fit ordinary fermion, but does. So if you want, zeta prime is t plus c dagger. Therefore, it doesn't get a minus sign. Zeta double prime is I times c minus dagger.
Okay.
Okay. So what I did here is, if you square this, you get something like ULUR K, ULUR K. And then you bring this K across, you get ULUR, UL bar, UR. And you bring this UL bar next to the UL. And thereby, if the two commute, then you don't get anything. If they anticommute, you get a minus sign. Yes?
Confused when the symmetry is unitary and when it was anti-unitary. B was anti-unitary, right?
That's a discussion. Because for the second one, it's less obvious.
For the general statement over that's or we wrote ULUR, but in general, the Q was anti-unitary, we would write ULUR.
Yes, I did, yeah, that's right. So I didn't show the most general situation.
Sorry, what is K?
What is K? Complex conjugation. Complex conjugation. Okay, and that's what I did here. This bar means complex conjugated. So once I square it, I get this combination, and I know that this thing has to be 1. But now, depending on whether I acquire the minus sign by commuting these two guys, I have a minus 1. Okay. So this means that there are three possible invariants that we can have. Because we want to make this thing here, so we want to have, we have this condition, in addition to this condition. Yeah, p squared equals 1 ultimately. So what we have is possibilities. Let me write out this. It's 3 exponents, so it's 8 possibilities. Possible projected representations, which can be defined by 3 possible exponents. PL PR equals -1 to the A PR PL, where A is essentially 0, 1. 0, 1. We see here that additionally U bar L UL is -1 to the B, and U bar R UR is -1 to the C, where E and C are also just Z2 objects. So you have 2 times 2 times 2 possibilities, which is 8. So I told you that the König type explicitly constructed this interaction which opens the gap without breaking the symmetry. But you can infer from the symmetry fractionalization, if you have time reversal symmetry and this feminine imperative symmetry, that indeed there are only 8 possible topological manifestations.
Shouldn't the classification also depend on some other symmetry that is a product of this symmetry, like some chiral?
In principle, you can look at what the product does here, and it has no impact in addition. I think that's the statement. So you're right that in the temporal wave classification, that's what we're usually looking at. Here, this is enough for what it is. Okay, so that concludes today, and tomorrow we're probably doing spin rotation systems.